Okay. Yeah. When I was younger, I was the same way, and when I was a new teacher, I was 23, and the music teacher said to me, she was older, she was in her 40s, and said to me, "Oh, you young people are always tired." I was exhausted. She says, "When you get older, you're going to be less tired." And it was true. I get less tired as I got older. But this morning, very tired. Okay, everybody seems to be completely and absolutely somewhere else mentally. Okay, is everybody here? No? How many people are not here? Raise your hand. Okay, that's the entire class said that. Okay, so what I want to do first is I want to give a complete and absolute overview of electron configuration, quantum numbers, the whole ball of wax. These guys are going to be shocked. Okay? Yes? All right? The first thing I want to do is I want to draw a periodic table. Okay? So the first thing you do when you draw a periodic table, you draw the first column. Okay? Now the first column is going to have 7 blocks in it. Okay? And you're going to want to do this. 2, 3, 4, 5, 6, 7. Okay? You're all going to want to do this, trust me. All right? Then the next thing you're going to want to do is you're going to want to make 18. You're going to want to make 18 columns. Lizzie, you're going to want to do this, so get some paper out, okay? Okay? And then you're going to try to do 18 columns. 1, that's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. All right? So that's 18 columns. All right? Mark, can you go in my office there, and on the left, on the counter, you're going to see some paper towels. I need something to make sure things are erased. Okay? So the next thing I'm going to want to do is I'm going to want to make 18 columns. So that's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. And then I want to bring these over, okay? Bring these over. So this is essentially a grid which is 7 by 18, okay? 7 by 18. And then you want to make 2 rows here. You want to make 2 rows at the bottom. Okay, you want to make 2 rows at the bottom that are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay? You want to make sure 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay? Okay? And then you're going to want to outline the table. This goes down 1, over, down 2, over 10, 3, 4, 5, 6, 7, 8, 9, 10. And then up, 2, over, and then up 1. Okay, that's your table. Now you can get rid of the rest of it here. Okay. Now what I can do is you've outlined it, and that's okay, and that's good. That's your table. Your table is the red outline. Now you're going to have to. I'm going to erase this because I can do that because I have a whiteboard. Okay? That's what I got. Yes? So that's your table. Okay? Now what you could do, you could number this 1, 2, 3, 4, 5, 6, 7. And you could say that this is 1, 2, this is going to be 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 10, 11, 12, 13, 14. You know what, that looks very sloppy. Let's do this instead. We're going to label this as 2, and then we're going to label this as 13, 14, 15, 16, 17, 18. Okay? And this is going to be 3 through 12. Okay? So that's 10. This is 10 columns here. Clear? Are we all set with that? Now, what's the problem? Yes. 14. 14 columns. Now, now you've all had a lot of chemistry in one form or another, either in 7th or 8th grade or in biology last year, correct? And you know that this table contains elements. And these elements combine with each other to form molecules, ions, formula units, all the time. Yes? And you've heard of something called ground state. Ground state is the neutral state. It's not a stable state, but it means the number of protons equals the number of electrons. Okay? Ground state. And when we first look at the periodic table, we're not going to look at the periodic table in terms of something that necessarily reacts. We're going to look at basically ground state. But what we do want to look at, in addition to ground state, is if an element does react, why does it react? Why does it react? Anybody? Why doesn't it react? Why does an atom react? Why does a neutral atom, for instance, sodium. Sodium is number 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It has the atomic number is 11, so the atomic number means what? The number of what? Protons. The number of protons. Excellent. So in its ground state, it would have 11 protons and 11 electrons, correct? Now, we know that it reacts actually violently with chlorine to form sodium chloride, yes? Okay. Why does it react? Because it wants to react? Do you ever wonder why it reacts? What does it want? It wants to be stable, obviously, that's why it reacts. But how does it become stable? What is the definition? What is the definition, two-word definition, of what stability means relative to the periodic table? Yes?
A full outer shell.
A full outer shell, I like that. A full outer shell, okay. Enzo?
But it fulfills the octet rule.
It fulfills the octet rule, I like that a lot. The octet rule, these guys know a lot of chemistry. Okay, yes? Yes, and you do. Trust me, I know you do. You're so bright, you're going to do aces in this. Okay. Okay. Now. So what elements fulfill the octet rule on the periodic table by their just mere nature in terms of ground state? Which ones are in ground state but they're not reactive at all? Yes.
Noble gases.
The noble gases. And where are the noble gases? What column number?
18.
The column number 18. Now, have you ever thought about this? That it's not necessarily the octet rule why atoms react. They react because they want to be like a noble gas, right? And then you look at then you look at the noble gas and you say, wait a second. The noble gases have a full outer shell, except helium, which has a full first shell, right?
Yeah.
Okay, but we don't really. So The octet rule doesn't really work necessarily. What does work is this, Lauren. What does work is this, Abby. You ready? And it's very simple. You ready? An atom reacts to be like the nearest noble gas, period. So if the sodium gives up an electron to be like the noble gas, neon, which is the closest, right?
Down one.
Down one, sorry. No.
Yes.
Yeah.
No. Sodium is going to has 11 protons and 11 electrons, correct?
Yeah.
Now, it's going to be like the nearest noble gas, which is neon. We don't even need, we just need, you know what we need? We just need the blank periodic table, don't we? We don't need to name things. We don't have to say it's neon. This block wants to be like this block, right? You see that? We don't need names for them, right? The first day of school, do I know your names?
No.
Can I still teach you?
Yeah.
Of course I can. So names are unimportant, really. Now, this is significant. Are you ready? This is very significant. The most important thing about the periodic table is the blank periodic table and the positions of the rectangles relative to each other. That's what's important. And when we come back from Eid, you're going to have a quiz. And you know what that quiz is going to be? Being able to construct this. Just like this. 18 columns, 7 rows. This one has 7, this one has 6, down 1. This has 4, between like that. Just like this. Just exactly what I have on the board. You don't have to put any numbers in. You just have to build from memory. And all it's going to take is 2 or 3 practices. It's really kind of easy. All you have to do on the quiz is construct a blank periodic table. We are not going to put elements into the periodic table for about a month, maybe 3 weeks. We're not going to put elements in the periodic table. We're just going to work with blank periodic tables. Because the point is this. If you can see patterns in the periodic table without the elements there, just those patterns will tell you the chemical and physical properties for the rectangles that are blank.
Periodic table pretty much tells you everything you need to know.
Excuse me?
The periodic table pretty much gives you everything you need to know.
Lauren, that's wonderful. God bless South Africa. Yes, that's correct. She's from Pretoria, one of the capitals of South Africa. They like to have 3. Did you know there's 3 capitals of South Africa? Did you know that?
No, this one.
Pretoria. Maybe they changed it. Did they change it?
No,
Used to be Johannesburg, Pretoria, and Cape Town. One was administrative, one was judicial,
Yeah.
one was
oh, but those are not capitals.
executive.
It's like-
It's all together in Pretoria now?
It's not, no.
Excuse me while we talk about South Africa a moment. Yes.
It's not capitals, it's just like,
Regional governmental centers.
Yeah.
something like that.
Yeah.
Okay.
It's always been.
All right.
Geography,
Regional
Victoria,
governmental
Cape Town
center.
are known for specific things.
Okay, understood. So let's get back to chemistry, but thank you for that. Lauren said that the periodic table contains everything you need to know. It does. It's amazing. I could tell you on that periodic table if something is a gas or a solid just by looking at the position of the elements. Reasonably. I could tell you the reactivity of those elements on the periodic table just from the position of the
Atomic
rectangles.
mass units.
I could tell you so many things just from the position. Now, what we need to do is this. This is what we need to learn today. Big task. It's going to take a few days. We need to know what are the charges that these ground state atoms acquire when they become like the nearest noble gas. We need to know how the electrons are distributed around the nucleus. We need to know the quantum numbers. Now, that may sound like a big deal in Schrödinger's equation, but quantum numbers are actually very simple. Quantum numbers are coordinates. In other words, the periodic table, think of it this way, write this down. The periodic table is a map, and each rectangle has 4 coordinates. Each rectangle has 4 coordinates. And the 4 coordinates are as follows.
S, P,
You ready? The 4 coordinates are as follows. N is the principal quantum number. N is the principal quantum number. N, as in Nancy, is the principal quantum number. You ready? L is the shape quantum number. The shape quantum number. M is the magnetic or orientation quantum number.
Like L.
I'll repeat it. S is the spin quantum number. So let me repeat that. Each rectangle has 4 coordinates. We call them 4 quantum numbers. N is the principal quantum number. S is the shape. M is the orientation or the magnetic. And S is the spin quantum number. Now, those are all in your book. Okay? Now, this is important. This can become very complex. If you take IB chemistry or college chemistry, those quantum numbers will become more complex. But what you can do with those quantum numbers is you can identify each square. Now, just so that you're not nervous about this, remember you're 10th graders, correct? Yes? Yesterday, over 2 or 3 days with 8th graders, I did this whole thing, this whole lesson, and every 8th grader was able to do it. Trust me when I tell you, let me finish, and I'll tell you I'm finished, and then if you want to worry, you can worry. But don't worry until I say that I'm finished, okay? All right, now, so this has one electron, so we're going to ignore hydrogen, is that okay? This has 1 electron away from being like neon, 1 electron away from being like, helium. 1 electron away from being like helium, 1 electron away from being like neon. I'm getting confused here. 1 electron away from being like argon, etc. You get that? So all of these elements in that first row are, if they gave up 1 electron, they would be like the nearest noble gas. They would have the valence shell. Are you ready for this? What's a valence shell?
The outer shell.
The outer shell, but I'm going to make it a little bit more complicated, already, and this is very important. Mr. Nair left this out of the explanation when you were in 7th, 8th, and 9th grade because it's a little bit more complicated. So I'm going to tell you 2 things. Lauren, you said the first thing, that the valence shell is the outer shell, but it contains, are you ready for this? This is you're not going to understand this, okay? When I go like that, then you should understand it. But if I don't go like that, then don't worry, just write it down, okay? The valence shell contains the S and P electrons. And you're going to understand what that means. Trust me. Just write it down. Everything will become very clear. You go to Paris and you see someone riding on the sidewalk and they've just begun and you say, what are they doing? They're just making a mess on the sidewalk. You come back 3 hours later, all of a sudden it's very clear what they did, right? I'm not pretending I'm an artist. Trust me, I'm not an artist. I can't sing, I can't draw, I can't paint, and I only know English. But I can tell you this, I know models, and I'm trying to show you a model of the atom that makes its behavior predictable. That's what we're doing today, okay? Are you with me? Okay? So the valence shell is the S and P electrons, the outer shell, right? So these all will give up 1 electron. So this will have, for instance, this will have, if it gives up an electron, it will have, what's the atomic number of this? 3, right?
Yeah.
Lithium. If it gives, and it has 3 protons?
Yeah.
So if it gives up 1 electron, it'll have 3 protons and 2 electrons. What will its charge be? +1, right? No, not negative because it gave up an electron. This isn't accounting. This is electrostatic charges. It's going to have 3 protons and 1 less electron, correct?
Yeah.
So that'll have 11 protons and 10 electrons, correct? So what will this entire column become? What charge? +1, right? +1? Are you with me? Okay. So this will be plus 1. What will this column become?
Plus
Plus 2. What will this column become? Remember,
2. Plus
that has 13 electrons. If it gives up 3,
Plus 3.
it'll be like the nearest noble gas, right?
Yeah.
Is it going to give up 3, or is it going to take on 5? What makes more sense in terms of probability? Give up 3, so what will its charge be? Plus 3. What will this one be?
Plus or negative?
Plus or negative 4. You get that?
Yeah.
It'll be plus or negative 4. Let's go above it. This is plus 3. This is plus 4, negative 4. Right?
Yeah.
This will be minus 3. I'll just finish it. You get it? Abby, you with me? Not yet? Okay, you're going to get this. Okay? Abby, do you see that this column, that column, this has, look on a periodic table. Do you have a periodic table there? Look over there. Look to the left. No, one right there. What's that element?
F.
F, that's right. What's the name of that? What's F? Fluorine? Okay, F is fluorine, right? Okay, you don't know? Okay. Okay, but do you see that as one away from being like this? You see that as one away? You see that? So if it gained 1 electron, it would have an outer shell just like this, right? What's the charge of an electron? Do you know that? Charge of an electron is negative 1. So if it gains a negative 1 charge, what's it going to be? It's going to have a negative 1 charge because it has the equal number of protons and neutrons. It has 9 protons and 9 electrons. That means it's 0 charge, right? So if it gains 1 electron, what's its charge going to be? Negative 1. There you go. These are all going to be negative 1. That's what that negative 1 means. That's all. That's all. Nothing more than that. It's very, 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 very straightforward. Okay? Trust me when I tell you this. I am going to explain this until every single person understands this. I'm not doing this once. I'm taping this, right? So you can look at it over and over and over and over and over and over and over again, right? And if you want to ask me a zillion questions, I will give you a zillion answers. Okay, you with me, Annabelle? You sure?
I don't understand now.
Okay. You understand? You getting it? Okay, good, excellent. Now, so we get the charges, right? Now, the next thing. There's 4 sections to the periodic table. I'm going to erase some of this stuff. Is that okay? Because it's kind of in the way. Is that all right? Okay. There's four sections to the periodic table. There's 4 sections to the periodic table. There's the S section. There's the S section. There's the D section. I know you're going to think I was going to say P next, right? This section here is the P section, and this is the F section. This is an S. Why is helium? It's an S, but it's in the P. Why is that? Why is that? Why is helium here instead of here? Because, well, you're all correct. Outer shell's full. It's a noble gas. The reason is this: because yes, there is an argument that helium could be there. 1, 2, right? Yes, but this is why helium is over here. Helium's properties are so close to the noble gas that they put it there. You see this. When Mendeleev, Russian chemist, 1860s approximately, when he made the periodic table, he organized the elements according to what? We didn't know anything about electrons. Nothing about electrons. He made the periodic table according to properties, physical and chemical properties. So helium was placed here because its properties were consistent with that of the noble gases. Okay? Right? You got it? Now, I can put electrons in each of these sublevels. Okay? in S, which is made of one orbital, I can put 2 electrons. Right? That's the capacity for S. The capacity for S is 2. 2 electrons I can put into S. Okay? How many people already knew that? Yeah. Okay, now, for P has 3.
6.
I can put 6 electrons. All right? Yes? See, all I'm doing, have you ever played a game and you have no idea how to do it? Did you ever do that? Did anybody ever invite you to play a game, card game, board game,
Yeah.
athletic game, and you have no idea what you're doing? And what's the game made of? Rules, right? And once you learn the rules, you play the game and you think to yourself, wow, I can explain to somebody, Lizzie, how to play this game, correct? Yes, do you have a question? What is it? Yes, of course. Just take a pass, not a problem. All right, so that's all I'm doing. I'm giving you the rules, okay? Can you go that way, huh? Okay, so I'm giving you rules, all right? That's all I'm doing. All right, D.
10. Oh. And F is 14. I think.
And
With that, the orbitals come, right?
those are orbitals. Those are individual orbitals, okay? Are you with me? You with me so far? Okay. Let's stop this tape. We're going to call this electron configuration part 1. I think we've done a lot, haven't we? Yes? And we'll come back and do number 2. Yes? Excellent.